Hello, I'm Ryan Baker, and this is Big Data in Education, Quarantine Edition. In today's class, we'll discuss epistemic network analysis. Epistemic network analysis, developed by Schaefer and his colleagues, consists of studying relationships between elements in coded data. It's got a whole lot of applications, and it's got so many applications that it's largely the underpinning method around a conference founded pretty recently, the International Conference on Quantitative Ethnography. Epistemic network analysis is basically a form of network analysis, and as we talked about in the last lecture, in network analysis you have a group of nodes and a group of links. With an epistemic network analysis, nodes are occurrences of the codes that you're interested in, and I'll give a couple examples of that in a minute, and links are co-occurrences between the codes. Let's start with an example, and I'll be honest, I picked this example primarily because I understand it well. In this example, we were comparing students who quit a level in the game Physics Playground to students who don't quit a game level. And we're comparing them in terms of the gameplay actions each group of students makes. In the context of Karumbaya's work on Physics Playground, nodes are behaviors, and you can see here, for example, behaviors like erasing an object, drawing a pin on the screen, creating a ramp, nudging the ball. These don't really mean much to you, but these are the behaviors, and drawing a freeform object. And links represent when a player demonstrates both behaviors in one session playing one level. So if a student is playing a level right now and they both erase and draw a freeform object, we have a link between them. And you can see from this graph that a lot of students did both those behaviors in the red group, which I'll define in a minute. So if we look at this graph, we can see that when red students draw a freeform object, they also erase. And less commonly, the line's a weaker line, when they draw freeform objects, they also nudge. Now, when green students draw a freeform object, they don't do those things. The strong green line between draw, freeform, and ramp tells us that when green students draw a freeform object, they also draw a ramp. And less commonly, when they nudge, they also draw a ramp. Now, the two colors in the data allow us to compare groups in the data. So in this case, red signifies people who quit a game, and green signifies people who don't quit. And so we can use this graph to study the difference in behaviors and interrelationships between them, between people who quit a level and people who don't quit a level. Now, ENA allows you to do a lot of cool things. And one of the ones that Karumbaya did is she and her colleagues actually compared graphs between different contexts, in this case, level. So you can see that on the leftmost graph, the level flower power, there's a very different pattern of behavior than in the middle graph shark or the rightmost graph big waterfall. Now, as you can see, interpreting these graphs is a little bit tricky. It really requires domain knowledge, which, let's be fair, I haven't really given you all the domain knowledge you need. But it takes some work to interpret these graphs, but it can be really powerful for understanding when you really dig into them. But as sort of a demonstration of what you can do with this method, I'll now go through 4 key themes that Karumbaya and her colleagues identified. First, identifying the key action. The green players were more successful in identifying what action was really needed to solve each level. In the case of flower power, a ramp. In the case of caterpillar, a springboard. In the case of big water ML, a ramp. So being able to identify these meant that the player could get to the correct solution. And without these, the red players, they couldn't get to the correct solution and eventually ended up quitting. A second key theme that Karumbaya noticed was missing the identification of supporting objects. Objects like a pin that needed to be drawn so that the physics operators could actually function properly. Third, an over-reliance on nudge, an operator that doesn't really leverage deep understanding of physics by the players who were ultimately unsuccessful, seen in all 4 of these levels here and in fact many other levels. And finally, over the course of time, and these graphs here show from left to right students' progress over time in playing a game level, students who were unsuccessful typically didn't try as many actions and types of operators as students who were successful, and converged too early compared to the players who were successful, who tried out a lot of things and then converged. So as you can see, there's a lot that you can tell from looking at these graphs. But just like social network analysis, you don't have to just look at graphs qualitatively. You can also do statistical analyses of graphs. And in the particular case of ENA, statistical analyses of differences. So for example, if you want to look at link A and link B, and link A looks stronger, is it actually statistically significantly stronger? Or, for example, if we're looking at group R versus group S, say the quitters versus the non-quitters, is a link stronger in one graph or the other? By doing these kind of comparisons, we can really get a sense of what goes together and what doesn't and what the differences are. Let's look briefly at another couple examples of ENA to get an idea for the scope of kind of uses that the method has. Nash and Schaefer, for instance, studied how the connections between topics changed over time in meetings. When we look from the left to the right, we see different meetings that a team had with their mentor, and we can see that the connections strengthened and shifted over time. Arastapur and her colleagues studied the processes of successful and unsuccessful teams over time. Barony and Foster looked at student posts and how the text of them related to student identity, and then used that to look at how student identity changed over time. Now, there are a lot of questions you have to answer when you're setting up an epistemic network analysis, such as what actually makes a relationship stronger? A second key one is, what are your codes? And how did you derive those codes? People have done ENA from a variety of types of codes. Behaviors in data, like for example, the Karumbaya example we saw earlier today, text mining, hand coding, like the Barony and Foster example we saw, hand coding and then text mining using Kai et al.'s Encoder Plus package. There's lots of ways that people come to these codes. Also, you have to ask, what codes do you display? Do you display all your codes at once or pick a subset? That's particularly interesting. What are your aggregation units, called stanzas? Are they just everything a learner does ever? Or might they be everything a learner does in a specific situation or context, like the levels in Karumbaya? Or everybody in a group of learners or a team, like in the Arastapur work? Or everything in a piece of content? Or everything in a meeting, like the Nash work? As you can see, there's a lot of options for how you aggregate your data, and it gives you a completely different interpretability instead of things you can look at. How you choose to set up your model kind of comes down to what Schaefer and his colleagues refer to as stanza-based interaction data. A set of objects, the way they relate to each other, grouped into a set of stanzas that reveal evidence about the relationships between the objects. Another important question, and it's one you'll also see in social network analysis, is, are you looking at one-directional relationships or bidirectional relationships? Usually, like the examples we've looked at today, ENA is bidirectional, but some work does look at one-directional relationships over time. Finally, although there's probably other issues one could think about as well, you might ask, what do the x and y axes mean in the graph? I've kind of just bypassed that so far today. Typically, they're determined empirically by collapsing the feature space using SVD, singular value decomposition, which is a lot like factor analysis and also a lot like spectral clustering and a lot like support vector machines. This approach can make x and y hard to interpret, but it best splits out the variables visually. Other times, like in a couple of the examples we've seen, people will actually pick variables and make them the x and y axes for greater interpretability. So I hope you found this lecture interesting. ENA is, I think it's fascinating. It's an important method growing in its scope of usage and the community applying it. So that just about wraps up this week. There's another area of network analysis, knowledge graphs or knowledge spaces, that we're not going to talk about this week, but we'll come back to it in week 7 when we talk about Q matrices and ways to represent the interconnections of knowledge. So look forward to that. And that about wraps up this week. Next week we'll discuss visualization, which kind of blends smoothly from the fact that we've been talking about methods that involve visualization in this lecture. So thank you very much. I'm Ryan Baker. This is Big Data in Education, Quarantine Edition.